Now I'm going to introduce the next talk. It's my pleasure to introduce Dima Damen. She's a professor of computer vision at the University of Bristol. She's currently an EPSRC Fellow, and she focused her research in automatic understanding of object interactions, actions, and activities using wearable, visual, and depth sensors. You may know her because of the Epic Kitchens project. And she's also program chair in many computer vision conferences. I'll let you the floor.
Thank you very much. I like yesterday somebody asked me, "Are you Epic?" Like, yeah. So I think my name is now called like synonymous for the data set. Thank you for the introduction and for the invitation and for this very important workshop. And I like the name of the workshop is Limited Label Data. So I'm going to start by asking which really is more important. So we have these three things that we build our current computer vision and machine learning models on: data, labels, and then tasks that utilize the combination of the data and the labels to achieve certain missions. And I want to argue that we have limitations in all these three axes. So we certainly, in certain cases, have limited data, right? We can't get the data. Of course, there is the other extreme we all are aware of, which is we have the data, but we might not have the labels. But there is also the question of we might have the data and the labels and we're not asking the right questions. And over the talk, I'm going to kind of talk about these three things, particularly the limited data problem and our experience with the long tail problem, despite the amount of effort you might put into collecting data. Then, of course, I'll make more emphasis on the limited labels, but I'll also focus on our ongoing work on trying to think about how to utilize better the labels and the data that is available. And let's start with the first thing, limited data. And for those of you who haven't seen Epic Kitchens, I always tell them, if you haven't heard of Epic Kitchens, don't tell me. It kind of drives me mad. So I'm hoping the majority of you have heard of Epic Kitchens by now. And if you've heard of it and you haven't seen it, then this is the type of footage that we have collected by giving people cameras and asking them to go and collect. Basically, put your camera on before you walk into the kitchen and record everything in your own kitchen. And what this gives us is the ability to recognize certain actions. So, for example, we have enough examples of people in various settings, in various countries, opening their oven. And I always like the fact that it's natural. So the top left view is actually the heat that kind of comes into you when you open the oven that actually has been projected onto the camera. So this is the type of footage that we have. And for open oven, I think we're sorted. We can now recognize opening an oven anywhere using egocentric camera. But if you look at the data that we have, then this is what we actually are monitoring over around, a couple of minutes. You have these actions that are fairly long, like grating the carrots. This is following up by this very, very short action of putting down the grater. And of course, we have the truth, which is anything that's naturally collected is long-tailed. So the y-axis here is log scale. Don't let it deceive you. This is extreme. So we have a lot more examples of certain things than others. And this is the case of actions. And this is also the case of objects, right? So we have a lot more of certain things than others. The most common vegetable in Epic Kitchens and apparently in all of our cooking is onions. We've seen enough onions by the end, but there are lots of things that we might have seen only once. Right, so if we talk about images, then everybody understands this long tail or few shot problem, starting from I haven't seen any example to I've seen a few examples or synonymous with the word tail class to the I have seen enough. But I want to tell you that in videos, we have this other complex problem. In addition to the instances, we have the lengths of certain actions. And that really introduces additional complexity in learning. So you have these short and rare actions, like breaking glass, right? It's like instantaneous. But if you want to recognize it, you're not going to find enough examples and you're not going to find enough frames. Of course, there is the other extreme of things that are long and frequent, washing dishes. But there is the other thing that is short and frequent, like opening drawers or opening oven. But you have rare and long, like sharpening the knife. And why am I making the distinction that length really matters? Currently, it's because of the way we deal with videos in video settings. So let's take this not frequent, but long enough video of someone sharpening a knife. And let's see how our models deal with this input. Currently, up to my knowledge, unless someone had changed things, we sample a few frames from these videos and we feed them into whatever you like, whether it's a 3D or a transformer, but you still need to sample a few frames. And with these long actions, we can do these combinations of different samples, allowing us to really learn a lot, right? Because we have enough possible transformations. The problem is when I don't have enough frames. In fact, the short actions, in my opinion, or experience until now, are a lot harder than the long actions and offer another level of complexity in few data in videos that isn't really the same in images. Right. So long tail really introduces this additional complexity in videos. Short actions are really severely disadvantaged. And collecting more data doesn't help. So if you've heard about Epic Kitchens, you might have heard about this brilliant effort led by Meta AI and Kristen Grumman to collect Ego4D. And we've scaled from 100 hours to 6,700 hours, and we still have the same problem. This is log scaled. We still have the same long tail, and whatever you do, as long as you actually have a limited number of examples of something in the world. So that doesn't solve it. And of course, saying, I want to have a balanced model, let me throw the majority of my frequent actions, produces worse results. So we really don't know what to do with this next step. So let's talk about the current methods. None of them are real solutions that we have tried, and telling you what we're currently trying to explore. The one I am very passionate about, I call it compositionality in actions. And this is a paper that we've worked on a while ago, ICCV 2019, where we wanted to learn two different embedding spaces for verbs and nouns. So we basically take the sentence and separate the verbs and the nouns. And we only want to learn the verb, right? So the whole thing is about, is this a put or an open, regardless of the object? And then the other space is purely on nouns, regardless of the action. And of course, these two spaces, you can then go from them and combine the information, okay? Combine the information from these two embedding spaces into the standard space that we have. But by forcing the model to go via this compositionality, you're actually forcing the model to understand what is the action here and what is the object. So in this space, this is a very kind of simple model. You can think of it of any blocks. But the most important bit is the fact that the video is projected using two different projections. One projection that focuses on the noun and another different projection that focuses on the verbs. And then you can combine them in whatever favorite way. But if you look at the outcome of these models, and let's focus on one of these spaces. So this is the noun space. And you look at the activations for one neuron in that space, and you realize that it's actually figuring out all of these are chopping boards in different actions. It's actually managing to merge these into the same space, regardless of the actions. And if you look at the verb space, you find open and close of all sorts of objects put together. And that compositionality allows you to, of course, to do zero-shot learning, right? Because if I now know what's open, regardless of the object, and what's chopping board, regardless of the action. That's one way to go around the long tail. And we have been really working with plenty of the examples out there for long tail. And I can tell you, nothing really yet works on the extreme examples of Epic or Ego4D. So there is a real need for people to think about long tail in video. If that's of interest, we'll welcome your input. So I'm not going to talk more about the long tail problem. I'm going to move into maybe what most of us have been working on, which is the limited labels. And I'll start by thinking about limited labels, which is labels with limited effort as opposed to less labels. And that's one of the things we've done when we collected Epic Kitchens, which is to ask people to narrate the videos by giving us a rough timestamp around the action. So we don't have the very expensive start and end time. We have a rough thing around the action, and we call these timestamps. And in this work, we were starting from these rough timestamps and trying to learn a model. So the input is, roughly the action is here, and the output is now you have to learn a model that recognizes the action. So basically, what do? You start with a rough estimate of the action. So you still don't know, this is the initial thing. You sample certain frames, you train a model, then you figure out the response of that model, and you refine your estimate It's not a huge refinement because you know you're roughly around the same location until you exactly get the moment in time where someone is opening a fridge. And something I learned when we were working on this project is that when you do that, you don't get the start and end times that humans have labeled. You get these very peculiarly, unique discriminative moments. So if you have the example, for example, of, so this is the refinement over time. You can see these kind of proposals estimated, and you can see the ground truth. And in many cases, you get something a lot closer, smaller than the ground truth. You get the moment that someone is actually opening a drawer or moving a glass. You get something a lot shorter or more discriminative. So it's very difficult to deal with these if you want to go back and evaluate on our traditional start and end times, but it's a way forward. The next bit I want to talk to you about is domain adaptation. And again, we've done a lot of work with that when we collected EPIC kitchens, because we collected another version of the dataset 2 years later, and we realized that the models don't generalize. And that's 2 years later, not 10 years later. All the effort we've been putting in collecting data, imagine if in a couple of years, none of it will be really useful. So in this work, we were looking at actions specifically again, and looking at the multiple modalities that actions and videos offer and how these can be useful for domain adaptation. So we are looking at our standard 3D CNN here, and an RGB and an optical flow, training on a single environment where we have enough examples, and then trying to generalize into another environment. And we all know what happens, it doesn't work. But what's really shocking is the fact that these spaces don't even overlap. Like you look at the space and there is nothing really common between the RGB space of one kitchen and another, despite all your effort that you're training for certain actions. And in this work, this was actually CVPR 2020, the era where self-supervised was really picking up, and we just plugged it into domain adaptation. So what we have is we take modalities of the same action, modalities of different action, and this doesn't need any labels, right? Because you can even do that on the new kitchen with no labels. And just by doing this self-supervised exercise, you end up grouping the big red space that was the new kitchen into these actions that are similar to one another by doing the two modalities. And then with some adversarial knowledge, so this is a gradient reversal layer that attempts to stop the discrimination between the source and target. Eventually, you end up with doing really well. This is someone cutting in one environment and then someone cutting in the new environment, different object, different background, different chopping, different person. And if you rely on this source only, these are spaces that are very, very different. With the self-supervision, you get the clustering and they do get closer, but they don't fully overlap. And with the combination of the self-supervision and the gradient reversal, you end up basically recognizing this cutting environment, this cutting action in the new environment. Okay. So let's move into, I think the reason why I was invited to give this talk is because of our work last year on few-shot action recognition led by Toby, who's done a brilliant effort in that. And I learned a lot about few-shot and how few-shot is formulated through this work. So the concept of few-shot is as follows. You assume you have a fixed number, say 2 shots of one action. Let's go back to our examples of cutting. And you want from these 2 examples to recognize new examples of that action. And interestingly, the way this is currently formulated is very, very limited. You assume you have 3 actions and exactly 2 examples of all of your 3 actions, which is like anti what I was telling you about the long tail, right? We never have this exact, right? 3 ways, 2 shots. Apparently, this is how most of the few shot methods currently are formulated. So again, you have this support set and you're trying to learn a classifier using the support set, which classifies the query videos. And interestingly, all prior works in video have assumed that each video is treated separately in the support set. And in this work, we wanted to do something differently. We built this on something that was out there, the cross transformers out of DeepMind, which was really focusing on basically taking a query image and looking at evidence of the correspondence in the whole of the support set. So that was the first inspiration for this work. So basically you construct a class prototype from all the relevant subsets, and we wanted to copy that into all the relevant frames from the support set. But it's not enough to do that on individual images when you talk about actions. So we relied on another really old work that I really like. So this is ECCV 2018. if you haven't read Temporal Relational Network, go and read that. I think it still is very relevant, and we haven't picked up on that yet in transformers, where you actually build a representation from a different n-grams of frames. So you have 2-frame relations, 3-frame relations, 4-frame relations. And that's really important because some actions are more fine-grained than the others and thus require more samples to be recognized. So we put the two ideas together into what we call TRX, Temporal Relational Cross Transformer. And it goes as follows. You have your query video, say of 4 frames, and you have 2 examples in your support set of class 1. And we build these pairs. So we take 2 frames and we built a 2-frame query and a 2-frame key and value, basically. And we build that from the full support set. So that means we basically here have a transformer. You're trying to basically take the query as a combination of frames from your query video. These are the key linear map projections of your whole support set. This is softmaxed. And then you have the value linear map, and that gives you basically what we call a class prototype, i.e., how similar is this class to your query video? Of course, we started here by only a pair of frames from the query video. That might not be sufficient. Of course, you can compare that to the query, but we want to do that also for all possible combinations of frames. So what you have at the end is this representation of class 1, this representation of class 2, but that has attended to your query video to know what really is most similar. And in the paper, we think that, as we said, 2 frames isn't enough if you have fine-grained knowledge. So we try the same approach for triplets of frames. Similarly, you can produce triplets of frames and find the combination. This is not as heavy as it sounds, because basically most of the effort is on the backbone, which is shared. This is a small head on top of a shared backbone. And if you look at the results, then really this work last year clearly outperformed everything that's out there, and also showed us how people compare to different subsets of different things. So Toby kindly prepared a nice code that allows you not only to compare to TRX, but to things that have existed before us. And if you've used this work, then it's a very well usable GitHub repo. Critically, we showed that some datasets are a lot harder than others. So if you compare kinetics to something V2, which is a more fine-grained dataset, you see that looking at a single frame versus 2 frames versus triplets and 2 frames doesn't make such a difference on kinetics, but makes a huge difference on datasets like something. And critically, as in this work, we really focused on utilizing the size of the support set. And thus we have this thing that says maybe in one example or one shot, we don't outperform, but as you go into bigger shots, you clearly outperform. And we show that actually we are utilizing those other support sets. So this is the number of videos in the support set that queries utilize, with the majority of the queries utilizing at least 2 or 3 videos from the support set to make their decision. Okay, so basically, if you've seen this in the paper, you looked at it, what it does is that it says, this is the query, and this is the 2 frames in the query. And this is the best support for those 2 frames. And because we use something like temporal relational network, they need to have the same order, but they don't need to be next to one another. So these 2 frames match these 2 frames, etc. And we showcase that for examples like triplets, you can also get better understanding. And I think this is one of my favorite examples where you can see that the person is throwing the paper in their hand, and these 2 frames are things on the floor, which find support for things on the floor, and things in the hand, which cite support from things in the hand, because these videos have all these combinations. Okay, and again, another shout out for Toby's GitHub, which if you want to do few shot video, start there. Okay, moving further, again, there is a lot of emphasis on what can we do with limited labels, self-supervised or synthetic strings. And I want to tell you about UnweaveNet, which is a work we're presenting this CVPR on Thursday, led by Will in collaboration with Carl Bondrek at Columbia. Going back to EPIC, and I think one thing that at least has inspired my career is watching the data. So we have these examples of people waking up in the morning, you walk into the kitchen, you start preparing your coffee. So you put the kettle to boil, but while it's boiling, you're not really standing still waiting for it to boil. You go maybe and realize there are some dishes to wash, or you want to put the toast in the toaster. You basically interleave or move between different goals until you can achieve all of them. And that's how we operate. And from the experience of doing activity recognition for years, I know that this is not how we think models need to work with activities. We think the person is going to start making coffee, finish making coffee, and then start making food, right? And that's how most of our data sets and models operate. But if you collect data naturally, you realize that is not the case. And we wanted a model that replicates that understanding, can start from the very beginning, parses the video, and recognizes the switches between different goals. And this ended up being something very similar to what we've all learned in maybe year one of computer science. So we have basically a model that has two things. It has a controller. It decides what to do with the current clip. And it has a memory, which we call the thread bank. And these two together produce an estimate of what you want to do with the next step. The controller is a transformer. So basically, it takes these learned memory information of previous actions. It takes the current clip, and it learns projections of the threads and the clips, as well as this token for new threads, because you want to be able to start new threads as well. And this transformer then just basically contextualizes the clip with the threads and decides which of these best suits the current observation. And eventually, you can update the memory. A few things on UnWeaveNet, it looks like, why am I talking about that in limited knowledge? And I'll tell you why, because of the way we train this. This is trained end to end, because you really need to understand what clips and threads mean from the data. And it's trained in ways that language models have been trained until now. So teacher forcing, that means you fill the memory up till now with the ground truth, and you just train for the current decision. So at each time step, everything is populated by the ground truth assignment, and the loss is imposed on the current decision. When we realized we needed to train this end to end, we realized we will never have enough labeled data. And that's where we now relied on lots of this synthetic or self-supervision. So we propose self-supervised training for UnWeaveNet that basically starts by saying, okay, let me invent a story that has 3 threads. The first thread has 3 clips, etc. We're inventing something, and then we're taking one video and positioning our invented stuff into the video, right? So we kind of are putting something in the video, and these clips have some variability in distance and location. Critically, they are from the same video, otherwise it becomes a trivial solution. Then we really interleave them, making up this synthetic story, which we then use to train the model, because this is already, we've built this. So we know the decisions. Is this a new thread? Is this resuming a previously paused thread? Is this, etc. So we've built all of these, and we have thousands of these we can then train the model using. That's not enough, because that doesn't really tell you anything about goals and switches. But on top of this, you have a small number of annotated data that we produced, I think around 1,000 stories that we've actually labeled. And the combination of both makes a big difference. So let's show you the outcome. Let's show you this UnWeaveNet, what it does. This is now the inference. So we're watching a video, we're making a decision. So everything now is new. There is nothing in the memory bank. This is the number, the clip and the ground truth. So you're starting by saying, okay, I think the person is doing something. And then at a certain point, you can see this switch. So a new thread is more likely than the current thread. And then with time, you're kind of figuring out the person is moving from one thing to the other. It's really very hard to see them with the video. So Will has produced these visualizations of short clips with the clip index, with the prediction, the ground truth, and the decision score. And you can see the model basically saying, I'm still doing the same thing. And these examples are important because you don't want the model to just keep predicting, especially when there is large head motion, like stretching the pizza dough. But also, UnWeaveNet is capable of looking at the video and saying the person is dicing meat, then they go and rinse the cleaver, then they come back to dicing meat. And this notion of comeback and resuming doesn't exist in any of our problems until now. Of course, as well as other things. I'm setting up the motion meridian, then I'm clearing, then I'm washing my hands. Okay. How are we doing with time? Okay. We don't know how we're doing with time, so I can keep going. So next is, I have 20 minutes, fantastic. What questions? Next is the tasks. And perhaps you've seen this in UnweaveNet, is this notion of what do we actually want to train on? And we've had loads and loads of data, and we have been in many cases not asking the right question. Why? Because we don't know. I've told you about this long tail problem, right? So what do we do now? We either train with the long tail, and thus the long tail is killed. You know, if you look at any outcomes of epic kitchens or long tail data sets, you see that the tail recognition is 0. Or we go and kill the head, and we introduce this problem of few shots, as if the head doesn't exist, only have few shots. And we say, okay, that's how we work. We don't really know how to learn from the whole bunch of data, labeled or unlabeled, that we have. Worse, even when we have models that can utilize the data, we are unable to assess how well they do. And in action recognition, for a while, one of the problems we have is bias in the data, right? So you think you have correctly recognized the action, and then you go and look at what the model had learned, and it had picked up the handle of the cupboard as an example of something. It hasn't seen the action. So over the past year, we and the team have been working on these new annotations. So this is more labeled data, but its attempt is to understand models. So what you can see here are pixel level annotations, dense annotations on epic kitchens. And you can see the transformations of objects over time. And I'll just play a few of these. This is data that will be in the hands of researchers in a month's time maximum. If you know epic kitchens, then you know this is data that has been created by people without any instructions. And here we are annotating this data with dense knowledge. And again, this is suffering from exactly the same set of problems. It's long-tailed. It is spatio-temporally different. There are things that have very small pixels and very small time, and things that have many pixels and a lot of time. So what we're calling Visor, and this is a collaboration with the Universities of Toronto and Michigan, is 270,000 manually segmented hands and objects, which we have interpolated into more than 10 million filtered dense masks. It's still not a lot. It's 36 hours of epic kitchens. 30 hours will be released, and 6 hours will be the test set. And again, video object segmentation. So let's see what we have. Why am I introducing this? Because I think this is the long tail problem really exposed in truth. So this is what you will have with Visor. You will have these frames that have been labeled. You'll be able to have semantic knowledge. So you have the left hand, the right hand, you have the hob, you have the saucepan, you have the spice being poured, the spice container, the spoon that is occluded, the soup, and then what's in the hand, right? So you have every active object. You don't have segmentations of the rest of the image. Additionally, you have this additional information. So we also have this open vocabulary that we have mapped into a closed vocabulary of classes as well as macro classes. So that really helps in case you want to do more generalization. We also have what epic kitchens always had, which is action. So with every image, you know what the action ongoing is. We have knowledge of what the hand is in contact with. Is the hand in contact, and which object it is in contact with. And we also have the knowledge of if something have been exhaustively or non-exhaustively annotated. I'm going to show you just a video, and you can see that we haven't labeled every single image. We've interpolated them into dense knowledge, but we have these long-term understanding of actions and interactions. We have these segments, and we can see the object in action undergoing transformations. So the person is picking up the peeler, and then they're actually peeling, and you see the peel formed. They're peeling the other object. They're washing the peeler, and you can see the UnweaveNet concept going back and coming, clearing, etc., etc. So back to the same problem. You label pixel segmentations, the y-axis is log scaled, and you have the long-term problem. What do we do? How can we get rid of it? Of course, we also have the same problem of bias, right? If you have the link between actions and objects, you know that, when you're washing, there is a sink and a tap, right? These are related. You don't see them in other types of actions. But at the end of the day, unless we start really looking at the data we have, labeling it with enough information to be able to ask difficult questions, we will not be able to go forward. So there is limited data, there is limited labels, but we also need, but we also have the combination. So what am I presenting? I'm saying data will always be limited. Don't believe all this craziness that we have infinite amount of data. We don't, and people who've tried to collect data of birds and plants know that at the end of the day, you will have a lot of something, and you have something that is very, very rare. How to deal with that? Interestingly, people in machine learning don't want to deal with long tail. They believe that that's not their problem. So maybe that's a problem we need to address. We all know how that limited label is an issue, and we've found ways around it, whether it's self-supervision or whether it is trying to do compositionality. So that we're making progress with limited labels, but we're not making as much progress with limited tasks. And I think the combination of the three is what makes us move forward, at least in my humble opinion. Now, of course, I always get the pleasure of the invitation to come and present this work to you, but this is hard work of a large team over the years that have believed in trying to do fine-grained action understanding and have pushed me as well as the community to make sure that this is of interest. And I think I'm happy to take questions. Opinions are also welcome. Yeah. I have to repeat the question, don't worry.
Hi, I'm Dima from Nokia University. I have a big question. So basically, I just thought about even that we are on supervised learning services.
Yeah.
And this is the major oversight is labeling this, right? Without labeling, kind of really just crowdsourcing like many people that are wearing head-mount camera. Huge amount of unlabeled data and how we can solve the data issue.
So thanks to a collaboration of 11 universities, I don't know how to do that without boring you because I want to go back. Is there a way to scroll into specific slides this way? No? Okay. So that's what we've done with Ego4D, right? We went and said, okay, we were never big enough. Let's go and build this combination of different universities. So we have 11 universities. We collected data from 931 different people in 74 different cities. We asked them to collect a variety of things. What we ended up with is very much the same problem. So the long tail has not disappeared. Yes, this is the natural number of examples of certain things in the world. They're not exactly the same. For example, if you ask people to record what they do in their daily life, there are things you do a lot more than others. So what do we do with this data? Are we going to throw the head because we will never collect lots of examples of the tail? Right? So the problem persists. We can give people cameras, and we've done that, and we've recorded hours and hours, 6,700 hours. We still have exactly the same problem. We still have cases, sorry, I can't read these in detail, of activities that we only have 5 examples of. We have cases that have, it's interesting, like it's peculiar how similar this distribution is to Epic Kitchens, which is 100 hours, right? We still have the same problem. So what do? Either we have to throw the head or ignore the tail or deal with them separately, which is the few shot problem. Like say, okay, I'll focus on this, I'll ignore that, and I'll focus only on this. And that's the few shot problem. I don't think this is going to take this anywhere, right? It's unless we try to deal with the fact of life, we're going to remain stuck. And remember that I haven't projected here the other problem I talked about, which is actions can be long or short. I haven't repeated the question. I'm aware of that now. Yeah, the question was, what if we just collected more and more data? Give people cameras. And again, that's something we now became an expert of. We know how to give people cameras and how to think of all the ethics and other stuff, which is very critical as researchers starting in a new area like wearable. I think, there is at the end of the day, limited data of certain topics. You will never be able to say, that problem will be solved if you collect indefinite. And if you collect indefinite and do things like the current data sets, give me 100 examples of every class or 1,000 examples of every class, you're killing the head, because the head has 1,000,000 examples, right? Yeah. Does that answer your question?
Yes. Okay. Follow-up is, would this be a different challenge for few shots if we are scaling up the number of things?
So this problem is known as long tail versus few shot, right? Because currently the few shot problem assumes you only have few shot, unless the problem has changed since the last time I've looked. The few shot world assumes you only have few shot of all the classes. This is a problem of long tail. Some people call it open set learning, etc. The main concern here is, if you keep collecting, you will keep increasing this, but that shape is not going to change, right? And currently we have this assumption, as we said, that you have the same number. Few shot is about, I don't know, 5-way 5 class. Even if it is 50-way 50 class, it assumes you only have 50 of every class. This doesn't make sense. How can you collect exactly X number of exactly X classes? So again, we've worked on few shots and we published papers on that, and I think they are great papers, but I think the problem needs to be redefined.
So what about 5-way, like a unit of every 5-way?
Sure. 5-way 1,000,000 classes assumes you're going to throw the dates. The question was, what about 5-way 1,000,000 classes? But what about those other classes for which you have 1,000,000 example? You want to throw the 1,000,000 minus 5 and only keep 5? There are 1,000,000. You can just fish in the water and you're going to get them, right? Throwing them doesn't make sense.
And if you take them, then this would be a different, more challenging
problem. I think that my argument is we should form problems that match real life. If we form problems that don't match real life, they will remain as problems we can talk about in CVPR, but they're not going to really go further into solving real life. You're welcome. So I think that my final message is video is really, really hard. And I know many people avoid working with video because the learning curve is tough. You need more GPUs and all that kind of madness. And perhaps the way forward is collaborate with other people who want to do video, cluster and work on video rather than giving it up. It's really worth it. And it is where, well, life is video. It's not a static image. And so again, it has this additional dimensional challenge of long and short that I am yet to see that being even discussed or addressed. So it's a critical topic. And if you've worked on this and I haven't been aware of your work, please send me an email saying, we've done this, we've done it, we've thought about it, or I would like to work on this. Anything that solves long actions, short actions, few, rare, complex, I'm keen to look at, and or even an analysis in a paper of whether this method works in short versus long actions, which is yet to come into any benchmark, rather than, with all my love for kinetics, 10 seconds is the length of every action. That's again not true. Not true. There are 1 second and there are 3 minutes. Thank you for your time. Oh.
And so based on your understanding, what's the difference between those potential video and those output?
Third person.
And so this for both types of videos, we also like part of the
absolutely.
Yeah. So
No, the problem doesn't exist only in egocentric. All the truth.
Yeah. So
Yeah.
Based on your understanding, what's the unique part
On egocentric?
of the egocentric video?
In what I have presented, there is nothing unique about egocentric. All the problems of addressed exist in video understanding, whether it's third person, whether it's one on YouTube, right? So let's talk about some of the data set out there. Like how to 100 million. A brilliant work, and Antoine and Ivan and all the team have done a brilliant job. But what did they do? They collected, say, 100 examples of every task. But there are tasks for which there is only 100 examples, and there are tasks for which there are million videos. Okay, so again, the same question should be addressed. Why are we throwing all those 99,000 because we can only find 100? Yeah, that problem exists in all things. The length of actions exists in all things. Why am I passionate about egocentric? Because I think what it tries to address is the problem of untrimmed video, not edited video, right? So an untrimmed video introduces a lot more complexity than edited video. And I know we use the word video, but edited and unedited are different worlds. And I think unedited has more problems and things, but at the same time, it also has some solutions. If you look at someone opening a door from an egocentric perspective, the viewpoint looks the same every time. And if you do third person, it looks very different. So I argue egocentric is easier from the viewpoint independence concern, because you always see the thing you're cutting, you always see it from the same perspective, which I think is great. You have a bit of head motion, but you can deal with that. But most of what I said is a problem in video understanding, whether you're doing egocentric, sports, right? How many football matches can you find versus some obscure sport? How can we deal with the wealth of data we have that will never be the same number per class? Yeah, we know that doesn't work, huh? All these focal losses, they introduce something, but they don't solve it, right? Long tail is an unsolved problem. Anybody told you anything else? You know, I can argue for telling you it's an unsolved problem. And we're very far from dealing with long tail.
It's different from those lectures videos, right? And the challenge is that some we utilize those unique parts for our model design.
Sure, there are unique things in egocentric, particularly you focus on hand-object interactions. But again, the three problems I addressed, limited data, limited labels, limited tasks, is not specific to egocentric. But sure, egocentric offers an amazing knowledge into how hands impact the world. And that's what I like about egocentric. But even if you're not passionate about egocentric and you want to do video, please address those questions.